Hey everybody. Dr. Neff made a pair of really fantastic videos that go over pretty much everything you need to know in order to build covalent compounds, to understand covalent compounds, and to really take that step into understanding the fundamentals of organic chemistry that are going to be useful in a lot of different avenues in your future, regardless of whether you're studying chemistry in the future or not. However, I'm a physical chemist, which means I spend most of my time doing calculations and stuff like the things we did at the beginning of the quarter, and I don't know as much about organic chemistry. So here are a couple tricks I have for kind of cutting through and doing covalent structures in a pretty straightforward way. We're looking first and foremost at carbon, nitrogen, and oxygen. Hydrogen is going to fill in all of the extra spots. And we can relate this to everything we have on the periodic table. This is going to be really important, keeping an eye on where carbon, nitrogen, and oxygen are on the periodic table, how far they are away from having their full shell, all of those things. But really, when I'm looking at a structure, whether I'm trying to draw a structure or whether I'm grading structures you've drawn, I always look for the same pieces because there are very predictable bonding patterns that we can see from where they are on the periodic table. We'll start with carbon. Carbon has, grab your periodic table, figure out the valence electrons. Carbon, it turns out, has 4 valence electrons. And it needs 4 more valence electrons in order to get to its closed shell, in order to have its s orbital, its 2s and its 2p orbital full. So if we're thinking about this in terms of Lewis structures, we're always going to see carbon form 4 bond structures, whether that's a carbon with 4 single bonds, a carbon with a double bond and 2 single bonds, and that's 1, 2, 3, 4, 1, 2, 1, 2, 3, 4, a carbon with 2 double bonds, 1, 2, 3, 4, or a carbon with a triple bond and a single bond. These are the acceptable pieces. If we have one of these pieces, we're going to have a structure that's got good formal charge. It's going to have a stable electron configuration. It's going to have potentially some resonance structures, but this is going to be the things that make a good structure. It is possible that you have things besides this in a carbon structure. Carbon monoxide is a fantastic example, but those are going to be more unstable compounds. And this is where we really want to start with looking at stable compounds. If we're looking at nitrogen, on your periodic table, find nitrogen. It's 1 past where carbon is, so this is going to have 5 valence electrons. And we'll just go put those in. 1, 2, 3, 4, and I'll just put the 5th one there. It needs 1, 2, 3 more valence electrons in order to get its full shell, its stable configuration. So the easiest way to do that is to make something with 3 bonds. This can be a nitrogen with a triple bond, and that lone pair, we usually still leave that lone pair, the pair that is already together on there. It could be a nitrogen with a double bond and a single bond, or it could be a nitrogen with 3 single bonds. 1, 2, 3, 1, 2, 3, 1, 2, 3. Each one still having that double, that pair of electrons, what we call the lone pair on it as well. I'm not going to get into the fact that this is a cartoon representation of a very dynamic electronic system, but if we have compounds with nitrogen, these are the stable structures we look for. If you ever draw a nitrogen with 4 bonds, I'm going to scratch my head and look at that and say, that better have some extra energetic considerations. If you ever draw a nitrogen with only 2 bonds, there might be a better way to draw it. Again, there are exceptions. You could look at nitrogen dioxide. That's going to be a situation where you end up with nitrogen missing an electron. It's kind of a weird exception, but that's going to be a more reactive, more unstable compound as well. And these are going to be our stable compounds. Oxygen on the periodic table, you probably see the train coming at this point. 6 valence electrons. 1, we'll do it in the same way. 1, 2, 3, 4, 5, 6. Just going around filling in those valence electrons. That gives me 2 spots. Whether we want to think about this in terms of the Lewis dot diagram or in terms of the electron configuration or in terms of the molecular orbital theory, which we didn't get to, but whichever way we want to think about it, we end up with 2 places. And the easiest way to do that is to form 2 bonds. So in oxygen, we typically see oxygen with 2 single bonds and the 2 lone pairs, or you see oxygen with a double bond and the 2 lone pairs. These are what I look for when I am drawing a structure or grading a structure. If I see something besides one of these, I get suspicious and I have to go back to Dr. Neff's video and check the correct process for figuring out what is exactly the best structure. 85% of the time, though, the structures we draw are going to be using these pieces. So let's go ahead and look at drawing some structures. Let's go ahead and look at something that's going to have a combination of carbon, hydrogen, oxygen, and nitrogen. We're going to look at C3H7NO3. NO2. So we want to try and figure out what's the best way to put these pieces together in order to make a structure. Let's start just by putting a chain of carbons together. Let's throw a nitrogen in there as well. And the problem becomes where to put the oxygens. We kind of want to keep things with high electronegativity, the nitrogens and oxygens, a little further away from each other on occasion. So I'm going to go ahead and put an oxygen over here. And then I've got my 7 hydrogens, so I'm going to use the hydrogens to fill in the desired number of bonds on everything. We'll start here. 1, 2, 3, 4. Notice now this nitrogen has 3 bonds. I'll put 2 lone pairs on it. This carbon has 4 bonds. This carbon has 4 bonds. This carbon only has 3 bonds. 1, 2, 3, 4, 5, 6. And I've only got 1 more hydrogen to put on. So in this situation, I cannot satisfy both the carbons and the oxygens with just 1 hydrogen. So I'm going to throw in a double bond. There's nothing that says I don't have a double bond, so I'm just going to try a double bond and just put my last hydrogen there. This carbon now has 4 bonds. This oxygen has 2 bonds. It's 2 lone pairs. And this should be a good structure. Based off of the trends we just learned, carbon has 4 bonds, 4 bonds, 4 bonds, 3 bonds, 2 bonds, 2 bonds. All of these have the correct pieces for making a good structure. There are different ways we could draw it, but this is a completely fine structure. It's not exactly the structure that we usually get with this, but this is fine. And we can do the line drawing representation of this, where we say every place where there's a bend in the line, that's 1, 2, 3 carbons represented. I would put the nitrogen on there as well. Notice I have to have a bend, that's a carbon, that's a carbon, that's a carbon. If I just put the nitrogen at the end of this line, that would make it 2 carbons with a nitrogen attached. Possible. Off of this carbon, I want to do a double bond to oxygen and a single bond to an oxygen hydrogen. So any place, and I still, in Gen Chem, like to put the explicit lone pairs. So any place where there's not an element written, that is to say any place where these Benzar, those are assumed carbons, and it's also assumed that every carbon has enough hydrogens to give it the patterns that we recognize. We typically don't write in the hydrogens explicitly unless they're on other elements and we're trying to accentuate them in particular. But this would give us the line drawing. It's a bit more of a condensed way to write down the same thing. Also, this just makes it easier to see the bonding patterns that we expect and the ways we can make isomers. So this was kind of like my first kind of jump at it, but we can pretty easily also make an isomer of this by taking this carbon and just putting it into the chain. So we can do a carbon, carbon, nitrogen, carbon, oxygen, oxygen. Fill in the hydrogens. Now, it probably looks like I did that really quick. But again, I was just looking for those common patterns that we see in order to draw these structures. And what we've got here, let me make that a bit more clear, kind of ran into my own picture. What we've got here is an isomer of our other structure. That is to say, we've got two things, same molecular formula, but the structure has changed. So these are going to be two isomers. This one, where I drew that H a little sloppily, this one is going to be alanine. This is actually one of our amino acids. The name amino, we haven't learned all the functional groups yet, but we've got an amine group, and we've got a carboxylic acid group, so aminoic acid, amino acid. All of them have those functional groups, and that's where the power of organic chemistry, understanding functional groups and drawing Lewis structures, really starts to get us information about really relevant things in our day-to-day lives and understanding all kinds of materials around us. Let's do another example. This time, I'm going to draw a structure, and you're going to tell me if it's good or bad. We can do this two different ways. Let's see. I'm just going to, I don't know what I'm going to draw. Is this structure good? Is it bad? What's wrong with it? I have no idea what I just drew. I just started throwing things together. After you practice with this, it actually becomes a little difficult to make bad structures, but I did my best to make a bad structure. I can see 2, 3. I can see 2 definite problems and 1 kind of problem with this structure. Hopefully you can see them as well. From our patterns, that carbon doesn't have enough bonds, right? Since I explicitly wrote this carbon, I should explicitly write the hydrogens off of it. If I wanted to have the carbon, the hydrogens assumed, I would put this as a bend in the structure. Each of these, let's also figure out the molecular formula associated with this. So that's one problem. Another problem, this nitrogen only has 2 bonds to it instead of the 3 that we typically see with it. I did put the full lone pairs on this, so it still has 8 valence electrons, but in terms of the electronegativity, ionization energy, and how it likes to share its electrons in order to get a full valence, this is not our typical stable piece. And we're going to want to see this with 3 bonds around it, so we're going to want to change it somehow. We can't just throw in a double bond here because then the oxygen is going to have too many. So those are 2 definite problems. For our next piece of practice, I've got a formula. I'm going to draw a couple Lewis structures. You're going to determine which Lewis structures are valid, which ones are invalid, and why they are invalid. Also, take a moment, pause the video while I'm drawing these, and just draw your own as well. So, which ones are valid, which ones are invalid? How do we fix the invalid ones? And what do we have represented here? We'll start with this one. We'll kind of go in backwards order. It's completely fine to have rings. Those are things that exist as long as we are satisfying this structure. I'm going to go ahead because I have trouble when I was first learning this. I had trouble seeing all the hydrogens. So I'm going to go ahead and draw in the explicit hydrogens. You notice this H2N is just because I want to show that the nitrogen is directly bonding to this carbon. In this structure, if you count the hydrogens, we've got 2, 4, 6, 7 hydrogens. So this one needs more hydrogens. The structure by itself is completely valid, but it's not actually for this formula, so that's no good. You'll also notice it doesn't have enough carbons. We've got 1, 2, 3, 4 carbons, not 5 like we're supposed to have. So we need another carbon. We've got an alcohol group, we've got an oxygen in a ring, that's okay. We've got the nitrogen-hydrogen groups, those are fine as well. I think we could actually fix this structure just by introducing a carbon. Actually, no, that doesn't do it, does it? 2, 4, 6, 8. Oh, you know what? That does do it, because look what I forgot. There's a hydrogen there. Because I want this carbon to have 4 bonds. That's 1, 2, 3, 4. There's a hydrogen. There must be a hydrogen there for it to have its full pieces. So we've got 2, 4, 6, 8, 10. So adding that extra carbon in creates one of the structures that a structure that works for this. Whether this is a real thing or not, that's not what we're worried about right now. We're just working on drawing the Lewis structures. Let's check this one. We've got 1, 2, 3, 4, 5. So we've got all 5 carbons. I'll go ahead and draw in the hydrogens explicitly, remembering I need one there as well. And then we'll count up our hydrogens and oxygens and carbons. So we've got enough carbons. We've got 2 oxygens. Oh. I drew most of these without enough oxygen. So this one also needs oxygen. Right? This one still actually isn't done yet. I need to put an oxygen in someplace. in order to make this a stable thing. Fortunately, one of the easy things we can do is we can just, any place we've got a hydrogen, we can put in an OH, make a little alcohol group there. So now this has the 3 oxygens. Counting is important. Bookkeeping is important. Coming up to this one, nitrogens, we've got our 2 nitrogens. We've got 2, 4, 6. Whoa, we've got a lot of hydrogens. I think we've got too many hydrogens. 2, 4, 6, 8, 10, 12. We've got 12 hydrogens and not enough oxygens. So what I'm going to do, I need less hydrogen, more oxygen. Besides the fact that I need more of these things, this is actually a fine structure, just not for the formula we're looking at. So I've got to go ahead and fix that. Notice everything's got the pieces that we like, so I'm just gonna, I'm guessing I need another double bond or something in order to make this work. Unless I'm counting wrong. 5, that's good. Okay, yeah, I need to add something in. I want 2 less hydrogens, 1 more oxygen. Well, that would work. It makes a kind of strange structure. I don't think this would be stable in nature, but in terms of having a valid Lewis structure for this formula that we want, we've got our 2 nitrogens, we've got our 1, 2, 3 oxygens, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. That's a valid structure. Here in this one, again, putting in the explicit hydrogens, also where this line just kind of sticks out into nowhere, that's actually representing a CH3, a carbon with 3 hydrogens attached. Again, right away, I didn't put enough oxygens in, so we've got to add another oxygen in someplace. I think I forgot what I was trying to draw, but I was trying to make mistakes, so that's probably for the best. In terms of number of hydrogens, we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it needs, so I don't know how much needs, let's just say less, there have to be less hydrogens in this structure. So what I'm going to do is I'm going to make something that kind of looks like this thing above, and I'm going to put in a carbon-oxygen double bond right there. This makes a nice functional group called a carboxylic acid. That takes care of the needing more oxygens, and it also gets us less hydrogens, but I don't know if it's enough less hydrogens. So let's count again. 3, 4, 5, 6, 7, 8, 9, 10, 11. I still need 1 less. So we're going to have to do something for that. And also, I'm not a fan of having this nitrogen-nitrogen bonded up here. There's nothing that says we can't do that. But just from familiarity with organic compounds, I'm going to move that. Well, let's not move it, but just that catches my eye of something that looks weird. It is a valid Lewis structure, but in terms of does it actually exist in the world or not is questionable. So if I need to get less hydrogens, we need to put in a double bond someplace. Or a ring or something, right? We need to do something. We want to make sure we're using all of the good pieces. Oh, here's a huge problem. That's why that looks weird to me. How many bonds does this nitrogen have? That nitrogen had 4 bonds. That's why it looked weird to me. And you'll notice, once you get good at seeing patterns, you'll have those things where you have a hunch if something looks weird, and if you don't look closely, you won't notice. But At this point, we can look at this and say, oh, that's why we've got too many hydrogens. Let's just erase one of them. Because in my mind, as I was trying to rearrange it, I couldn't figure out how to rearrange it to just get rid of one hydrogen. And that was because I accidentally had something with too many bonds. And so if you don't have those good pieces to start with, or you don't have them in your mind, it's really easy to go down the wrong path for a really long time. Let's look at this last structure here. Putting in the explicit 1, 2, 3, 4, 5 carbons, so that looks good. 1, 2, 3, 4. We got 1, 5. Okay, we got 2, 4, 6, 8, 10 hydrogens, right number of hydrogens. 1, 2, 3 oxygens. This amine group might want to move over just to get away from that electronegativity. But in terms of structure, in terms of Lewis structure, that is a valid Lewis structure, even if the compound doesn't exist in that form. And you'll notice the speed of identifying what's right and what's wrong, and the ability to kind of recognize the pieces that make up the structures really speeds up this process. So, looking back at our pieces that are stable, we want to look for these types of things, and we want to be using these types of pieces to make our Lewis structures for the organic compound.